So for today's lesson, we'll be looking at how to read a Hertzsprung-Russell diagram. So let's begin by looking at exactly what that is. An HR diagram is named after Ejnar Hertzsprung and Henry Russell. That's the Hertzsprung-Russell HR. It's a graph that astronomers use to help understand stars. Across the bottom, we plot the star's temperature, and down the side, we plot the star's absolute magnitude. By charting stars this way, we begin to see a pattern. A star's temperature and color depend directly on how big the star is. A bigger a star is, the hotter it will be. This is because the stronger gravity of larger stars causes them to burn their fuel more quickly, raising the star's temperature. So how can gravity make a star burn its fuel faster? Well, the stronger an object's gravity is, the more power it has to pull its mass inward. This causes the core to be very compact and creates a lot of extra pressure. This extra pressure builds up, raising the temperature of the core. The hotter the core gets, the more of its hydrogen fuel it will burn. So this is a sample Hertzsprung-Russell diagram. There's some things that are different about these diagrams. They look difficult, but they really are pretty simple. One of the more simple things we do this year, they just look a little crazy. If you look, then usually this would be 0. On a Hertzsprung-Russell diagram, the highest number is to the left, and then it works its way down. So the hottest stars are going to be to the left of the diagram, and the cooler stars are to the right. Here we have brightness or luminosity increases as we go up the diagram. So if you were comparing just brightness, Sirius B here would be dimmer than, let's say, Deneb, which is higher up on the chart. Deneb would also be slightly hotter than Sirius B because it's a little bit to the left of where Sirius B is. So we just use this to compare stars. When we look at the Hertzsprung-Russell diagram, we need to remember the color of the stars. So blue or blue-white stars are the hottest stars. So stars in the 20 to 50,000 degree range are going to be blue or blue-white color. That's the color we're going to see if we were to look at those. So you should notice again that the temperature axis goes from high to low. The hottest stars are blue or blue-white. The next hottest stars are going to be in the 10,000 degrees Celsius section, and they will be white. Our middle of the road or average temperature stars, which include our sun, are going to appear to be yellow. If you notice, our sun is right there. Also, this section in the middle, that diagonal section that starts with Barnard star and goes all the way up to Zeta Eridani, those are our main sequence stars. Next, we're going to have our reddish orange colored stars, which are going to be around between 4 and 5,000 degrees. And then our red stars, which are going to be our coolest stars. And I know for some people that goes against what you think. You usually think red hot, blue cold, but for stars, they're going to be exactly the opposite. Now, to refresh our memory on luminosity, that was one of our vocabulary words. Remember that both the size and temperature of a star determine how much radiation energy it gives off each second, and that is the actual brightness or luminosity of the star. So luminosity is going to increase as we move up the y-axis on the HR diagram. Absolute magnitude is a measure of the brightness of an object independent of the distance at which it is viewed, which means it's the actual brightness of a star. So if we were staring at the 2 stars from the same distance away, we could determine absolute magnitude. Whereas apparent magnitude is how bright the object appears to be based on where the viewer is. So it's based on the distance from the viewer. So some stars appear very bright to us because of the distance. So in summary, we have this HR diagram here. We kind of look at what we went over. So it's a scatter plot basically, and hopefully you've seen scatter plots in your math classes. I remember teaching them back in elementary school. When we look at the HR diagram, here we know that the diagonal section in the center is the main sequence stars. We see at the bottom, we're going to have the white dwarfs. Now, don't let the name fool you because the white dwarfs go across many different colors. So in this one, Sirius B, Procyon, and Van Hanen star are the white dwarfs. The giants on this HR diagram are Capella, Arcturus, and Hera. You can see the dotted line circling those. And at the very top, we have our supergiants, and on this one it features Deneb, Rigel, Canopus, Polaris, and Betelgeuse. Don't say that 3 times or Mr. Reiner will show up. Alright, so just keep in mind that the numbers go backwards, that they start with a big number, go down to the small number, and the higher a star is on the HR diagram, the brighter it is. You can keep those in. We're going to get some practice in. It's easier if you just do it and kind of figure it out than explain it. It's really simple, though. I think a lot of you will be really successful with this. So make sure you remember the hottest stars are blue, the coolest stars are red. The higher a star is on the Hertzsprung-Russell diagram, the brighter it is. The lower it is on the HR diagram, the dimmer it is. Most stars in our universe are main sequence stars, meaning they're in the prime of their life where they're still burning hydrogen as fuel. So they're not dying out, they're not swelling up and dying or becoming giants. Absolute magnitude is the actual brightness of a star, whereas apparent magnitude is how bright an object appears to be based on the distance. And also remember that our sun is a yellow, medium-sized main sequence star located at the edge of the spiral-shaped Milky Way galaxy.
It's a deep, dark world beyond the planet Earth. Many planet stars make up the universe. Morning sun will rise, and into night it turns. I look up at the sky, put that in a verse.
Yeah, floating clouds of space dust and hydrogen, they're nebulous. If something irritates them, their life isn't so regular. The center starts collapsing from gravity, it becomes heavier, and under the pressure and heat, all of the hydrogen atoms will meet. Yes, they were born and they start to evolve. The nuclear fusion creates a new star. Protostar, that is the name that it's called, until it can grow from a kid through a doll. 50 million years it could take, after the atoms have formed a new core. Man, it be taking so long just for protostar babies to finally grow up and mature. Galaxy, yeah, that is the name. A system of stars in the far outer space. Galaxy, yeah, that is the name. Many different stars all over the place. There's red dwarfs, they're small, cool, and red in color. They live long for billions of years, they sit and hover. There's supergiants and giants too. These stars are hotter but color is blue, burning through energy fast until after a few million years their light's already through. But give me 1 second, there's a star that I keep forgetting. The sun in the sky, our secret weapon, set in the middle of star spectrum, an average star on the galaxy edges.
Beyond the planet Earth, many planet stars make up the universe. Morning sun will rise, and into night it turns. I look up at the sky, put that in a verse. And it's a deep, dark world beyond the planet Earth. Many planet stars make up the universe. Morning sun will rise, and into night it turns. I look up at the sky, put that in a verse.
Hydrogen burning now. The core of a red dwarf is cool enough. Subtracting the layers will loosen up. Now we watching it die and its time is up. When a red dwarf dies, it's a white dwarf. After all those years and the lights off. When a big star dies though, oh no. See the star turn the sky into a light show. Giant core going in, it's collapsing, its energy lagging, but then it explodes in a whole different fashion. Matter of fact, it's called a supernova. For a short moment blast, then what'll happen? It could turn into a black hole where it caves in and gravity pulls and everything. And even the light can't escape from its grasp. It's mad strong. But what if the supernova did something different? Electrons and protons will come together. Result is a neutron star existence. Small and dense, but the star glistens. And from the dust of a supernova, we could even form a nebula. And back to the beginning, we go to one. A new star is born and more to come.
Deep, dark world beyond the planet Earth. Many planet stars make up the universe. Morning sun will rise, then into night it turns. I look up at the skies and I put that in a verse. And it's a deep, dark world beyond the planet Earth. Many planet stars make up the universe. The morning sun will rise, and into night it turns. I look up at the sky, I put that into verses.